What if there's not a correlation though? The calculator will still spit out information for the regression equation, even if it tells you that the p-value is real big and there's no correlation. But you have to be very careful. If we say that there's not sufficient evidence for a correlation, then you should not be using an equation about a correlation. Essentially, if you're concluding that there's no correlation, then that equation is worthless. It's talking about a correlation that's not there. So don't use it if you've determined that there's no correlation. In those cases, if there's no real pattern, the best you can really do is say, well, it doesn't really depend on, let's use the car as an example. It doesn't really depend on the weight of the car, but I can tell you the average miles per gallon. Best you can do is an average. So in those cases, if there's no correlation, you cannot use the equation to make predictions, but you can at least average the y values and give that. You can either do that by hand, or you can do one-var stats on L2. So you'd go one-var stats and then L2 before you hit enter. So what you're essentially saying is this equation is not a good one. I can't use it. Best estimate I can give you is the average miles per gallon for cars. So if you did not have a correlation, we would not have used that equation to make the prediction. So let me kind of give you an example in that situation. So this is also from the last section, so you may want to pause and put this information back into your calculator under Stat Edit. These were data for test scores and performance ratings. It doesn't really matter what they stood for, but we had concluded that there was not sufficient evidence of a linear correlation. The pattern in the sample data was not strong enough to say that there was a correlation in the population. So we're going to find the regression equation just to practice finding that, and then we will estimate the rating of a person with a test score of 8, keeping in mind that there is not a linear correlation here. So stat test down in linreg t-test, you will find this regression equation, y hat equals, there was an A of 26.399. Actually, with the 3 significant digit rule, I could have made that 26.4, but more is okay. Plus a slope of 0.266 times x. So that's the regression equation. That's the equation that best goes through those dots. However, we had determined that there was really no linear correlation there. So this is pretty much just a line going through a bunch of dots all over the place, and they don't really tend to be close to that line. So we can't use it. So instead, we're going to need to just give the y values stood for performance ratings. We just need to give the average performance rating and say that that's the best we can do. So you are averaging the y values because you're trying to predict a rating. So this is just a quick screenshot to remind you we've done calculating means and standard deviations on 2 columns, and I think we've seen it on a second column as well. But stat calc over to one-var stats, or down to one-var stats. And then after you type in one-var stats, you need to hit second 2 to get the L2 in there. And so that will run an average on your second column. It'll call it X bar, but actually, since these are Y values, it's actually Y bar. So you should write down Y bar equals 29.3. So in this case, you don't actually, because there is no correlation, the question says predict the rating of a person with a test score of 8. You actually don't use that 8 because there's no correlation to test score, so you can't plug the test score in anywhere. You just say, well, the average rating is 29.3. That's the best estimate that I can give. So that's one example of a time when you want to be careful using that equation. There are some other things that you need to think about. You want to make sure this is already just an estimate. You want to make sure that it's as good an estimate as it can be. So the first one is just a reminder, only use that equation if the hypothesis test told you that there was a correlation. So you always have to do a hypothesis test first on these. Also, only plug in x values that are within the range of the original sample data. So what I mean by that is, let's say you had some weird 8,000-pound car. Well, we didn't have any cars near that, so you probably wouldn't want to use this equation to make predictions on it because you don't know if a car that heavy, that far away from normal cars, may not follow the same rules of highway mileage that the other cars do. That equation may not work for the really extreme values. So we won't be able to use equations for any x value that's not within that original range of data. It doesn't have to be in the data set, but it has to be within the range of those values. Some books do allow x's that are just a little bit outside, but fairly close. So we'll keep that in mind. So the third one says only use the regression equation to make predictions about the original population. So if everyone in your sample is a man, you cannot make predictions about women. If it's a mixed sample, then you can make predictions for people in general. But if it's all one gender, you can't make predictions about the other gender. If all of your cars are Chevys, then you can't make predictions about Fords, that kind of thing. And then just kind of a general thing, if your data is really old, make sure it's still valid. That won't be such a problem here in this class, but if you're ever, doing your own study, make sure that you're using good data. So we've learned several things here between these two sections. So let's just have one big example that kind of puts the whole process together so that you can see from start to finish how this all goes. So we've got heights and weights of 9 female supermodels. This is actual data. So their heights in inches and their weights in pounds. And so we're going to run through the process. We're going to determine if there's a correlation. If there is a correlation, we'll go ahead and write down the regression equation, interpret the slope, and then look at some estimates and whether or not we can make those. So first let's look at the hypothesis test. We need to set up the hypotheses, and remember these are pretty much the same every time when you're doing correlation testing. We're using that rho symbol, and the null is that the rho actually equals 0, so that would be no correlation at all, and then the alternative is that there is a correlation, so that rho is not 0. And then we're going to do a ln-reg t-test, so we'll say that. If you don't have that data in your calculator yet, you may want to rewind the video a little bit and pause and put that data in. You should, if you have the slides printed in front of you, you can do it there too. So ln-reg t-test, we get a p-value of 0.0103, so that's 3 significant digits. You do get to count the 0 in the middle. Once you hit the 1, you start counting, so 3 digits. If you gave more, that'd be okay though. Our significance level is 0.05. Make sure you check that, because if our significance level were 0.01, we would probably come to a different conclusion here. But our significance level is 0.05, and so our p-value is smaller than that. So for our requirements in this problem, it's small enough to reject the null, right? Because that's the probability that the null happens. So we're rejecting the null. That means you support the other option, you support the alternative, and there's no word fail in here, so there is sufficient evidence to support the alternative, which was a correlation. So there is sufficient evidence to support a linear correlation between the height and the weight of supermodels. And you could even put in the word all, of all supermodels, because we're using the sample to make inferences about the whole population. Because of that, we will go ahead and write down that ln-reg t-test screen also gives us the information for the regression equation. So we'll go ahead and write that down since we found a correlation. So, and it's actually a positive correlation because the slope is positive, if you want to say that. And the y-intercept was negative 151.7. With the 3 significant digits rule, you could actually say negative 152. I like to go at least 1 decimal place, so I did. So y hat equals negative 151.7 plus 3.88 is the slope times x. And so we've got that written down, and we can use that in the next slide to do some predictions. Remember, we're using y hat instead of a regular y because this is information from a sample. We are using it to make predictions about the population, but it's actually from a sample, so we use the y hat. Okay, the second question was to interpret the slope, and then we'll make an estimate. So interpreting the slope, it was 3.88. Well, the x values were heights, and the y values were weights. And the slope tells you when your x goes up by 1, what happens to the y. So as our height goes up by 1 inch, the weight, because the slope is positive, it's going to go up. The weights we expect to go up by about 3.88 pounds. So when a supermodel's height increases by an inch, we expect her weight to increase by about 3.88 pounds. Okay, it's always when the x goes up by 1, the slope tells you what happens to the y. And then C asked for an estimate. So supermodel who is 69 inches tall, checking the range of heights, that definitely falls in the range that we had. So we'll plug that 69 on in for the x, and we'll round to, I said you have to round at least as far as the y values in the data chart that you were given. So they were all whole numbers, so you can make this a whole number. You can go farther if you want. So 116 pounds. If you round your slope and your y-intercept differently from me, your final answer here could come out slightly differently just because of round-off differences, and I will be alert to that when I'm grading, so don't worry too much if yours come out slightly different because you rounded your other values differently. Now, part D asked, can we estimate the weight of a female supermodel who is 62 inches tall? Well, if you look at that chart, we only had models from 66.5 inches up to 72, shortest and tallest. And 62 inches is a bit outside of that, and we don't know if that short of a model might not follow the same pattern. In fact, I'm not sure you'd find too many models that short, but that means we're not going to be able to use this equation. So be aware of that, be looking for that when you're answering these questions. Part E said, can we estimate the weight of a male supermodel who is 67 inches tall? Well, 67 inches is within the range of the heights that we had, but all of the subjects in our sample were female supermodels. So no, we cannot use this equation to predict the weight of a male. And then the final one was, can we estimate the weight of a math teacher who is 69 inches tall? Well, 69 inches is within that. If it was a female math teacher, then could we do that? Well, no, because they were all supermodels. So unless your math teacher is sidelining as a supermodel, which she is not, you would not be able to use that for her either. So be careful when you're using these equations to make predictions, and make sure that you're dealing with the population that this sample was taken from, and that you're within the range of the data that you had in your sample.